Okay, in this video we're going to start looking at this application of oxidation states or oxidation. There's the set of guidelines that allow us to come up with these different fictitious charges. But I'll just show you, you've seen a few of these already on the periodic table. Most periodic tables have them listed somewhere, shown somewhere. Here's the oxidation state for lithium, for example. There's the oxidation state for beryllium. Now this is a little unusual, having a negative oxidation state for sodium, but the most common one for all group 1 metals is +1, as we'll see. So we get into the transition block and we see some other different oxidations. So look at all of them for vanadium, quite a few. Chromium has lots of possible oxidation states. Look at manganese, oh my goodness. So we're going to see how we come up with those values. If we go to the other side of the periodic table, then we have the nonmetals, and so notice first of all neon oxidation is 0. Again, makes sense, it doesn't react, but notice krypton does have a potential oxidation state of +2, so there's some electron transfer involved there. Chlorine, lots of different oxidation states. Sulfur, lots of different oxidations. Look at all of them for oxygen. Look at neon, only 1, and again that should make sense because neon has such a high electron activity. So I said something about this in the last video, but oxidation states or oxidation numbers, fictitious number. So you can't go to the bank with these numbers as being a charge. Okay, they're assigned by a set of arbitrary rules, and so it's just a way of for us to keep track of or help us analyze and more easily balance redox equations. And you're going to see that in practice in a little few videos from now. So the other important thing is an oxidation reaction does not imply that the element has acquired this as a charge. It's again simply a number for bookkeeping purposes, really, to keep track of the transfer of electrons. Okay, so as it says, it really does help us balance equations. So let's go through. There's 7 rules we want to be able to apply. So any element, when not combined with an atom of a different element, has an oxidation number of 0, and you saw this in the last video. So calcium, elemental calcium, 0. Elemental chlorine is 0. So that means in a covalent compound, both chlorine atoms would have oxidation states of 0. Iron, elemental, oxidation is 0. Xenon, elemental xenon, oxidation state of 0. So that's pretty straightforward. An element, uncombined, has an oxidation of 0. Makes sense. There has been no transfer of charge. Simple monatomic ions, that is a 1 atom ion, have an oxidation number equal to its charge. So magnesium 2 plus the ion would have an oxidation state of +2. Phosphorus 3 minus, the phosphide ion, has an oxidation state of -3. Okay, so again that makes sense because the implication is that it has gained or lost electrons, this ion, so the oxidation state simply matches that. But again, it's not a charge, and as mentioned last video, writing it backwards distinguishes it from an actual charge. So when we write oxidation, charge first, then the number. Step 3, or guideline 3. So this really applies to the metals on the left-hand side of the periodic table. So in any compound, the oxidation number of every group 1 metal is 1+. So here's sodium with bromine. So it's a group 1 metal. It always will have an oxidation state of +1. A group 2 element will always be +2. So calcium hydroxide, its oxidation state is going to be +2 in that compound. We're not going to worry about assigning the other states right away. Group 3, which is for the most part are going to be aluminum, will have an oxidation state of +3. So aluminum chloride, oxidation state of aluminum is +3. And so in lithium fluoride, well, lithium is a group 1 metal, so its oxidation state is +1. So this applies to those left-hand side of the periodic table metals, the alkali and alkaline earth metals. Guideline 4. In binary compounds with metals, the oxidation state of the non-metal is equal to the charge of its simple monatomic ion. So this is binary, so this is just 2 elements. We're talking about the non-metal here. That is, the non-metal with its higher electronegativity gets a negative oxidation state when combined with the metal. So these are binary ionic compounds. And again, so sodium bromide. Bromide is the nonmetal. The Br is the nonmetal. Its most common charge, being group 7, is -1. So bromine would be -1. Calcium phosphide. Phosphorus is the nonmetal. The phosphide ion will have is the ion, and the charge, most common charge for phosphorus, is -3. It's group 5. So it can gain 3 electrons. So there's the oxidation state for phosphorus, -3. And remember, that's assigned to each phosphorus. Aluminum chloride, well, chlorine's the nonmetal, so it gets its most common charge, -1 for a chloride ion. And lithium sulfide, -2 for the sulfur. Okay, so this is with the frame of reference around the nonmetals. So nonmetals with the higher electronegativity get their most common charge. All right. Guideline 5 applies to some 3 specific elements here. So in most compounds, fluorine is always -1. And again, it should make sense. It's highly electronegative. It is very unlikely. There's nothing that will be able to pull an electron from it. So it makes sense it should never have a positive oxidation state. And so fluorine is always -1. So hydrogen fluoride, fluorine's -1. Oxygen difluoride, fluorine is -1. We're going to see the application of material in a minute. Hydrogen is almost always +1. So in this case, hydrogen ends up being +1. And that's because fluorine is always -1. Hydrogen can't be anything but, because, as we'll see in a minute, the charge is 0. Now here's an issue. Oxygen almost always -2. So let's apply oxygen as -2 here. And what does that leave? Hydrogen. When those 2 of them, and the overall charge of the molecule is 0, so each hydrogen must be +1. So as it says, hydrogen is almost always +1. So in this case, combined with water, it is +1. Here's one with oxygen where it's not -2 though. We've already assigned the fluorines as having a -1 oxidation state. So oxygen cannot be -2 because the overall charge is 0. Oxygen must be +2. So as it says, oxygen is almost always -2, but sometimes it's not. Here's another instance, H2O2, hydrogen peroxide. So oxygen is almost always -2, but the hierarchy is we look at hydrogen first. Hydrogen is almost always +1, so hydrogen is +1. That means the oxygen atoms must be -1 in hydrogen peroxide, because again, overall adds up to 0. So this is this is when you have to kind of look at carefully. When you're involving these 3 atoms, if they're combined together. In most instances, though, they're always, as they say, fluorine -1, hydrogen +1, oxygen -2. In covalent compounds that do not contain hydrogen or oxygen, the more electronegative element is assigned an oxidation element that equals the negative charge it would have as an ionic compound. Now, I realize I have a couple of oxygens, so it still applies with oxygen. So sulfur and oxygen combined, oxygen has the higher electronegativity. So oxygen would get its most common charge, which is -2. That leaves sulfur, of which there's only one of them, to have a net charge, or oxidation of +6, because 3 times -2. PCl5, well, chlorine is more electronegative. It gets a -1 oxidation state, leaving phosphorus to have an oxidation state of +5. Here's one, P4O10. So again, oxygen is more electronegative. It gets its most common charge of -2, and there's 20- there's the charge, which means each phosphorus must have a charge of +5, because +20 and -20 add up to 0. Fluorine always gets its charge, which makes xenon, in this case, +2. So now you can see how you start applying multiple oxidation states. The sum of the oxidation atoms of all atoms in the form must equal a charge written for the formula. No written charge implies 0. Sum of the oxidation atoms of all atoms in a polyatomic ion must equal the charge of the ion. So this is basically what we've been going through. So oxygen gets its charge of -2. That -2 is applied to 3 oxygens. Each one is -2. The overall charge of sulfur trioxide is 0. So 3 times -2 plus some number for sulfur must add up to 0. So that number, that oxidation state, is +6. So +6 of sulfur. all adds up to 0. So that's what you're looking for, the balance, based on assigning an oxidation state that applies to all 3 of the atoms. You can't have a different oxidation state for any of these oxygens, so the oxidation state applies to all 3 of them. So sulfate ion, again, the oxygen gets a charge of -2. So the sulfur, well, the overall charge is -2 for the 2- for the polyatomic ion. So we have 8- from the oxygen. So we again have an oxidation state of +6 for sulfur, because +6 minus 8 equals 2- the charge. So that's what it means here. The sum of the oxidation states must add up to the charge. The dichromate ion, so again oxygen -2, and there's 7 of them, so that's 14-. There's 2 chromiums, and it has to add up overall to 2-. So each chromium atom has an oxidation state of +6. So again, +12 minus 14 equals the charge, 2-. Okay, yeah, hydrogen peroxide, remember we did this one before. Hydrogen is +1, oxygen is -1, so that's 2+ minus 2, and that equals 0. And the charge in a molecule is 0. Okay, so those are the guidelines. So a little bit more practice. So here's the acetic acid. So you can look at it this way, you can group them, and sometimes grouping is a little easier. So what are we going to do here? Well, hydrogen is almost always +1, oxygen is almost always -2, leaving us to figure out what it is for the carbon atom. So we have -4, 2 times -2. We have +4, 4 times +1. So each carbon atom must have an oxidation state of 0. Hydrogen sulfate ion, -2, +1. So the oxidation state for the sulfur in this case, we have +1 -8 plus something equals -1. So what's that something? That something is +6. So the sulfur has an oxidation state of +6. +1 plus 6 is +7, -8 is -1. That's how you get that. Sodium hydrogen sulfate. Okay, now we have 4 atoms in here. -2 for the oxygen, +1 for the hydrogen. Sodium, always +1 when combined. So we do have 3 of them right away. So now we have +1, +2, -8, sulfur again, -6. Beryllium cyanide. So we can look at this compound one of 2 ways. Now remember, beryllium is a group 2 metal, so when combined it's always going to have an oxidation state of +2. Now that means looking at the cyanide ion together can sometimes be a little problematic, so you can split it up. Remember, the cyanide is a negatively charged polyatomic ion. The more electronegative element is nitrogen, so it gets its most common charge, which is -3, which makes carbon +2. So +2 minus 3 equals -1. Just because there's 2 of them doesn't change the oxidation state. Alright, a little bit more practice. So oxygen fluoride ion. And so in this case, fluorine always gets the charge -1, which means oxygen must be 0. O2, 2-. Alright, so this is a polyatomic ion. This is not molecular oxygen. So there's 2 oxygen atoms with an overall charge of -2, so each atom must have an oxidation state of -1. Ammonium phosphate. So again, we have 3 ammonium ions, and so that can perhaps make things a little tricky. But don't forget, that's really what it looks like. And just because there's 3 of them, well, it is going to change the total charge, but it doesn't change the oxidation state within the ammonium. So you can treat ammonium by itself. +1 for the hydrogen, because it's almost always +1. -3 for the nitrogen. It's more electronegative. It gets its most common charge. So -3 plus 4 equals +1. So those are the oxidation states for the nitrogen, the hydrogen, and you can treat the phosphate polyatomic ion by itself as well. -2 for the oxygen, +5 for the phosphorus. So there are the oxidation states for those 4 atoms. Now this one is a little trickier, We've already seen that in the ammonium ion it's -3 and +1, but this is the nitrite ion, NO2 minus, and that's -2 and +3 for the nitrogen. So this is a case where you have the nitrogen atom has two different oxidation states in the same compound. It's a little unusual. It doesn't happen very often, but that's one instance where it does. So there are the 7 guidelines for determining oxidation numbers. The best way to do this is through practice. So you can copy these down if you like, or the best thing is to just start doing some problems where you're finding oxidation states. As it says, you have to familiarize yourself with the guidelines, and to do that it takes plenty of practice. That completes this video.